Hi there, today I'm going to start a new course about SIMATIC Manager software that can be used to program any PLC of S7-300 and 400 series of Siemens company. After a short introduction, I'll explain my PLC hardware, and after that, I'll show you a simple wiring diagram. Also, I'll explain how a simple program works in ladder language. Alright, let's start the video with this industrial automation pyramid to know what's the role of SIMATIC Manager or S7-300 400 PLCs in industries. As you know, in the lowest level of the industrial automation pyramid field, there are lots of electrical equipment such as push buttons, thermocouples, transmitters, motors, signal lamps, and other equipment. Naturally, we can't check all of them simultaneously and continuously. Today's PLCs are often used to accomplish this task. PLC is an abbreviation of Programmable Logic Controller. These devices help us to implement automatic controls in industries. Well, beside PLCs, some devices visualize industrial process for us. We call them human-machine interface, or HMI. Both of them need to be programmed by a computer. In this tutorial, you'll learn how a PLC of S7-300 or 400 series of Siemens company can be programmed using SIMATIC Manager software to control an industrial process. Alright, let me introduce my hardware. The main part or module of each PLC stations is its CPU, which is an abbreviation of Central Processing Unit. Actually, the CPU is the brain of the PLC. The CPU is the home for PLC logic, memory, and communications. Like the human brain, which is the source of our logical decisions, memory, and communications to the other parts of the body or other human brains. The CPU is where the PLC program is stored. I use a CPU of S7-300 series, CPU 315-2DP. If you don't have any CPU of S7-300 or 400 series of Siemens company, don't worry. You can use PLCSIM software to simulate and test your programs. Now let's learn different parts of a CPU. First, these indicators determine the status of the CPU and also some errors in the PLC station. On the right side, the bus fault LED indicates that there is an error in the system network, like a bad contact in one of the communication connectors, or there is an overlap between the addresses inside its network. On the left side, the first LED SF or system fault indicates there is an error in the system. This error could be software error, like an error in programming, or hardware error, like a power loss of one of the input modules. Okay, let's continue to learn what the other LEDs are. My CPU uses an external backup battery. The second LED indicates the connected backup battery is okay or not. When the next LED is green, it means the CPU is powered and an appropriate 5 volts is generated for the logic circuits and also for the bus for transferring data. When the fourth LED is steady yellow, it indicates that at least one of the PLC inputs or outputs is forced to on or off. Okay, the run LED is on whenever the CPU is working properly without any troubles and flashes in the startup of the CPU. Finally, when the CPU is in a stop mode or there is a software or hardware error, the stop LED is steady yellow. Note that for a memory reset request, it flashes slowly. Well, after the indicators, this empty slot can be used to insert a SIMATIC micromemory card. The next important part is this microswitch. I can use that to change my CPU mode among run P, run, stop, and memory reset. When the run P or run mode are selected, PLC executes its program. But there is a little difference between these two modes. When I put the microswitch in run P position, CPU can accept download a new program from my computer. But when I select the run mode, PLC will reject any changes and also the download option. Note that newer CPUs don't have run P position. They only have the run mode, but it's essentially the same as run P mode on older CPUs. Naturally, when the stop mode is selected, the CPU doesn't execute its program. Now let's see how I can reset my CPU. First, I select the MRES mode, about 2 seconds. Then I select the stop mode and again the memory reset mode. Now my PLC has reset without any program. Finally, at the bottom, you can see the order number of my CPU. Behind my CPU door, I access to its battery backup, its power supply connector, and also two RS485 ports. I use the first one to connect SIMATIC Manager software to my PLC and use the second one to connect my PLC to an HMI. After the CPU, I can use different types of modules for different purposes. I use 6 signal modules to receive or send digital and analog signals. Note that I can see the specifications here and also the order number at the bottom of each module. Note that there are lots of CPUs and modules related to S7-300 and 400 series of Siemens company. I recommend that to read their catalogs carefully. For example, here I can see some specifications about my CPU. Or in this user manual, I can find useful data about S7-300 modules. For example, let's see the wiring diagram of a signal module which has 8 digital inputs and 8 digital outputs. Now, after installing and wiring modules based on the catalog, let's see how a PLC program works. Like the previous diagram, this module supports 8 digital inputs and 8 digital outputs. I can assign these addresses to these inputs outputs with SIMATIC Manager software. Now consider this simple program inside the CPU. It works like this simple circuit. Well, when I press the first push button, 24 volts appear on the first input. Then its corresponding contact in the program, I0.0, change to close. Therefore, the CPU turns on its first output, Q0.0, like the electrical circuit. Alright, I've explained my hardware and also how a simple program works in a PLC. Now I'm going to tell you some initial and important points about PLC memory, scan cycle, and different operating modes. Okay, we program PLCs to control industrial processes. Therefore, they need to restore electrical equipment status by receiving their electrical signals. So, Let's see how a PLC stores this information on its memory. Many electrical devices have only two modes. PLCs can store these two modes on a bit of memory, which is the smallest unit to store two numbers, 0 or 1. Also, many devices have more than two modes. For example, an industrial motor can have three modes: clockwise rotation, counterclockwise rotation, and also its stop mode. Analog devices which work with analog signals require more bits as well. In consequence, PLCs use more bits. 8 bits together, which is called a byte, can store 256 modes. In other words, 1 byte can store a number from 0 to 255. See the table. I can store 0 with 8 zeros, 1 with 7 zeros plus 1 at the end, and similarly 2, 3 till 255. Note that if I change my rule to store numbers, I can have another range. For example, let's use the last bit to determine the sign of numbers, 0 for positive and 1 for negative numbers. In consequence, and such as the new table, I can store negative numbers too. Numbers represent industrial parameters such as speed, level, temperature, and so on. If we need more precision, we can use 2 bytes, which is called a word, to have 6553 modes. Note that there are a lot of standards to save data, such as numbers, time, date, using bits. I'll explain and use them later. Now, let's see the memory structure used by S7-300 or 400 CPUs. These CPUs use three important types of memory frequently: input image memory, main memory, and output image memory. Let's start with the main memory. Well, this table shows the main memory structure. We use the letter M for that. In this table, the first column shows byte numbers. For example, M2 refers to these 8 bits, and also M5 refers to these bits. As you see, each row has 8 bits that are numbered from bit 0 to bit 7. As I mentioned, many devices have only two modes, and 1 bit is sufficient to store their status. For example, M0.6 refers to this location on the main memory. The letter M refers to the main memory. The next number determines the byte number, and after the dot, the second number determines the bit number. Similarly, we can use any bit of the PLC memory, such as M1.4 and M5.2. Okay, to use 2 bytes, in other words, a word of memory, the W letter is used between the letter M and the first byte number. For example, MW0 refers to the first and second byte on the PLC memory, or MW30 consists of these 2 bytes, M3 and M4. Pay attention. If we use MW3 to store a number, we shouldn't use MW4 to store another number, because these two addresses have 1 byte in common, M4. Similarly, we can use the D letter to use double word, in other words, 32 bits. For example, MD2 consists of these 4 bytes, M2, M3, M4, and M5. Now let's see how a number like this, 7281, is saved on an address of the main memory like MW3. Note that this address consists of 2 bytes, in other words 16 bits. The least significant bit is M4.0 and the most significant bit is M3.7. Therefore, the green binary numbers are stored on the bottom byte, M4, and the red part is stored on the above byte, M3. Let's see another example to store a bigger number on 4 bytes on the main memory. When this address MD1 is used to store numbers, the least significant bit is M4.0 and the most significant bit is M1.7. So the selected number is stored with this pattern. Note that PLC fills extra bits on the left side with 0. Alright, we can use the two other memory types, inputs and outputs image memories similarly. But instead of the M letter, we should use I and Q letters respectively. S7-300 and 400 CPUs use these two memories to store the status of all inputs and outputs. Now let's see how inputs and outputs image memories are used. When a PLC is in the run mode, it reads all inputs and stores them on the inputs image memory. Then the PLC executes its program completely to determine the status of all outputs. Note that the status of the outputs on its image memory can be changed during the program execution, but the PLC updates the status of its connected equipment to its outputs when the whole program is executed. PLCs repeat this cycle to control industrial processes continuously. This cycle is called a scan cycle. Now let's see a flowchart which shows an overview of how the user program is executed during each scan cycle. PLCs have an operating system and we can load our program as the user program. When the power supply is switched on, the control processor checks the consistency of the hardware and parameterizes the modules. Then the startup program is executed once if present. Usually, user programs are divided into individual sections called block, which are OB, FB, and FC. Let me introduce these blocks briefly. OB is a short form of organization block. It represents the interface between the operating system and the user program. The operating system can only call organization blocks for specific events. For example, OB100 is called and executed once when the operating mode of the PLC changes from the stop mode to the run mode. Usually, the user program is long and complex, especially for industrial purposes. Therefore, we divide it into some function blocks and functions. Later, I'll use them and explain their differences. After the startup mode, in the run mode, the operating system first updates all PLC outputs and then reads all inputs. After that, executes OB1 cycling till the PLC is stopped. So OB1 is used to write the main program and execute it continuously. Every time an interrupt occurs, the operating system calls its appropriate OB and then returns to the main program. As I mentioned in the previous slide, this cycle is called a scan cycle. For a simple program, it takes about 2 or 3 milliseconds. Alright, let's see what CPU does during these 3 modes. When a PLC is in the stop mode, its CPU doesn't execute the user program, but it handles any communication request, for example, a request to download a new program, and also performs self-diagnostics. As you see in the startup mode, CPU does 6 tasks, named with A to E letters. A clears the process image inputs, in other words, clears the inputs image memory. B initializes the process image outputs. C processes the startup organization blocks, such as OB100. D copies the physical inputs to the process image inputs. E queues interrupts to be processed in the run mode. And the last item, F, enables the physical outputs to be changed. Okay, now let's mention the task which the CPU does in the run mode. In this mode, CPU first updates the physical outputs. Then it reads the physical inputs and updates its inputs image memory. After that, it runs the user program. This starts with OB1 as the main programming block. Also, CPU performs some self-test diagnostics in this mode. And every time an interrupt occurs, the operating system calls appropriate OB and then returns to the main program and responds to communication requests. Note that the CPU executes all these tasks cycling until the PLC goes to the stop mode. Now I want to start a simple project with SIMATIC Manager software. During that, I'll explain how the wizard window can be used to create a new project, and also how a simple program can be tested without any real PLC using the SIMATIC Manager Simulator PLCSIM. Okay, let's double click on the SIMATIC Manager icon. Okay, at the beginning, the wizard window appears automatically. From here, I can disable or enable this window or click here to close it. Let me explain how it can be used to create a new project. Naturally, each PLC station has at least one CPU. For now, let's select this one, CPU 315 2DP. After that, I can assign a name to the selected CPU and also determine its MPI address. Okay, after selecting the CPU, I can determine which organization blocks I will need to use in my project and also my preferred language for them. By default, the OB1 block is selected as the main block. It's executed cyclically when the PLC is in the running mode. Notice I can click here to see more details about each organization block. I explained OB1, so let me select another one. For example, OB81. Okay, OB81 is executed whenever an event occurs that is triggered by an error or fault related to the power supply or the backup battery. I don't want to use this block right now, so let me return to the wizard window. Another useful organization block is OB100. This block is executed once when the CPU is going to be started. At the bottom, there are three languages: a statement list, ladder diagram, and function block diagram. I can choose one of them for the selected organization blocks. After that, I can choose a name for the new project and finally click on the Finish icon to create my new project. Alright, I created my new project based on the selected settings on the wizard window. This is my project name, which includes only one SIMATIC 300 station with this CPU model. It only has two blocks, OB1 and OB100. Remember, the wizard window is accessible under the File menu. Also, an empty project can be created using the new item. Okay, I added this SIMATIC 300 station using the wizard window. I can also right-click on the empty space and add other stations manually. For example, if you want to hide and test your programs without any hardware, you can select this item, S7 program. Similarly, let's add a SIMATIC 400 station. Note that I'm recording this course based on an S7-300 CPU, but most of the contents of the course can be used for SIMATIC 400 stations as well. Now let's write a simple program and test it without any PLC. As I mentioned before, OB1 is the main organization block. It can be found inside the blocks folder. Otherwise, you can right-click and add it. When I open it for the first time, this window appears. I can determine a symbolic name or a comment for that. Now let me select the ladder language diagram and then click on OK to open it. Alright, whenever I double-click on each block, this window appears. Here I can write my program using the ladder elements on the left side. Now let's use a bit of the input image memory and also a bit of the main memory to activate a bit of the output image memory. Okay, as you see, my program is similar to this electrical circuit. Let me test it. Now I wanna test the program without any PLC. First, let's click on this icon to launch the simulator. As you see, here is a CPU with three modes: stop, run, and run P, as well as a real CPU. Well, let's have a better view by changing the size and position of the window. Also, let's go to the view menu and enable this item, always on top. Okay, let's continue. I need to select the connection type between the virtual CPU and my computer. For now, select the MPI port. Also, I can click here to reset the CPU. Now, let's select the OB1 block and download it to the virtual CPU. Okay, this message says the OB1 block is being processed by another application or another user. So let me close this window and then continue the downloading process. Because my project only includes a simple and short program inside the OB1 block, it was downloaded quickly. As you see, to test my program, I need an input module, an output module, and also I need to access this bit of memory. So let's use these icons to add the desired modules besides the virtual CPU. Well, pay attention to these addresses. For example, I can use this window to access the 7 bits of the first byte of the main memory. M0.0, M0.1 till M0.7. Alright, I've transferred my program to the virtual CPU. Now let's click on this icon to enable the online mode to see how the program is executed on the CPU. As you see now, the virtual CPU is in a stop mode. Let me run it. Now I can use these virtual modules to test my program. Also, when the online mode is selected, I can right-click and change the status of the addresses related to the main memory. Notice this way cannot be used to change the input addresses like this one. Okay, let's stop the CPU and disable the online mode. I've tested this simple program using the SIMATIC Manager simulator. As you see, for the SIMATIC 300 station, there is an S7 program folder under its CPU. So I can easily copy the contents inside this S7 program folder, like the OB1 block, and use them for the other stations. Now let's reset the virtual CPU and transfer the SIMATIC 300 station project into the virtual CPU. Note that compared to the previous project, the SIMATIC 300 station has a CPU and also an empty block, OB100. But their main programs inside the OB1 block are the same. In consequence, the performances of these two projects are the same. Okay, the SIMATIC 300 station was transferred into the virtual CPU. Let's test its program using the simulator. Alright, in this video I'll explain the wizard window and also how a program can be tested using the SIMATIC Manager simulator without any PLC. In the next video, I'll start a new project and configure my PLC station manually inside SIMATIC Manager. Also, I'll test a simple program with that. Thanks so much for watching this video. I'll see you soon.